Welcome back to ECE 320A. We're in Unit 11, which is our active filter design unit. And homework number 11 is due at the end of this unit. And the material that is consistent with this unit is Chapter 15 on active filters. And today what we want to do in this video is actually design a first order low-pass filter, and it's going to be active to achieve a specific bandwidth and to use a particular capacitor value. So here's what we're going to do, and this is a basic op-amp circuit. This is figure 15.1. It's first order. We have one energy storage device, but here what we have is we have a feedback impedance that I'm labeling Z sub F, and we also have an input impedance that I've labeled Z sub I, and you can see that Z sub I is just R sub 1, and Z sub F is in fact a parallel combination of R sub 2 and this capacitor. What we want to do with this circuit layout is figure out what R1, R2, and C need to be to satisfy or to achieve the following specifications. Actually, we already know what C is going to be. We want it to be a 1 microfarad capacitor. But with C being 1 microfarad, we also want the bandwidth to be 100 hertz, and now we have to make sure that we're working consistently with hertz or radians per second, etc., and we want a gain of 2. So we need to pick R1, R2, and C to meet these specifications. C is given, but that C, together with these resistors, might influence the pole location, and these resistors and capacitors might influence the gain. So we have to figure out how do we select these three parameters in order to achieve or accomplish what these design specifications are wanting or requiring. So the first thing we need to do is actually find the transfer function between the input terminals V sub I and the output terminals V sub 0. And the reason why I've gone ahead and labeled or dashed these particular quantities, Z sub F and Z sub I, is if we remember our basic op-amp configurations, we can actually write down immediately the transfer function of the op-amp. Do you remember if we had a feedback resistor and an input resistor, what the transfer function actually was associated with that op-amp circuit? And now all we're doing is we're generalizing that feedback resistor to be a feedback impedance and the input resistor to be, well, an input impedance, which in fact in this case is still an input resistor. So in terms of Z sub F and Z sub I, can you remember what the transfer function is actually equal to? And if you can't remember, then maybe what you need to do is write a KCL equation relative to this input node, or this node at the inverting terminal of the op-amp, and then from those, let's say a KCL equation, you should be able to find the transfer function, or one equation that contains V sub I and V sub O, take their ratio of V sub O to V sub I, and that will give you your transfer function. In fact, what you'll find is that this transfer function is now minus Z sub F over Z sub I. And if you don't remember that, and that's not that critical that you remember that, but you should be able to rederive that relationship. Z sub I, the input impedance, is just R sub 1. Z sub F is the parallel combination of those two impedances, R sub 2 and that capacitor's impedance, which is 1 over SC. Performing that parallel combination with two elements is just the product divided by their sum. And then in the last expression in that line of equations, we have simply put both numerator and denominator over a common denominator, which is little s capital C, and that's common to the numerator and denominator. Those can cancel, and we're left with then, for the feedback impedance, it's now a function of frequency, and it's R2 over the quantity S R2C plus 1. And now what we can do is we can simply substitute z sub f and z sub I into this transfer function equation that we've either re-derived or remembered of minus z sub f over z sub I. And since z sub I is pretty easy, it's just one element, r sub 1, and we're dividing by it, we can just divide that numerator in z sub f by r sub 1 and achieve the same result. Or what I'm saying then is v naught or v out over vn is minus z sub f over z sub I, which is equal to minus r2 over r1 over the frequency dependent denominator s r sub 2c plus 1. And now we have a transfer function. It's in terms of the three parameter values, r sub 2, r sub 1, and c, and what's the pole? Well, the pole is just, or poles, in this case we just have a linear polynomial in s, or an s to the 1 in our denominator, so we know we only have one pole. And the poles of our transfer function are those values of s that cause the denominator to vanish. In this case, if we solve that expression, s r sub 2c plus 1 set equal to 0, if we solve that for s, we see that the pole is now at minus 1 over r sub 2c, or since the time constant is actually this r sub 2c in this particular circuit, because we're in time constant form, we've normalized the denominator, or by default, the denominator was in time constant form. We have 1 as our constant coefficient. Then the pole is at minus 1 over tau, where tau is r sub 2c. Another quantity that we might want to have a handle on or express in terms of these three parameter values is the DC gain. We now know where the pole is in terms of R1, R2, and C. It's minus 1 over R2C. So we now know if we want to adjust the pole, we can manipulate R sub 2 and C. But we're already given C, so we'll get to that in a minute. But what about the DC gain of the filter? And here is our transfer function, h of s. What's the DC gain? Well, the DC gain is just the transfer function evaluated at DC, and DC is when s is equal to 0. Or if we look at replacing s with 0 in h of s, we end up with minus r sub 2 over r sub 1 over, now the r sub 2c goes away, because we're letting s equal to 0, or now our DC gain is now the ratio of that feedback resistor divided by the input resistor. And it's a negative because of the feedback actually coming in through the inverting terminal of the op-amp. But we're typically interested in the magnitude response, and so we can not worry so much about that sign in our transfer function. Let's now try to find a nominal or initial transfer function, and to do that, let's go ahead and set the r's to 1 and c equal to 1, and again, let's neglect the minus sign. So now h sub s is z sub f over z sub I under these different specific parameter values. So 1 divided by 1 is 1. That's our numerator, and 1 times 1 scaling s is just 1. There's now our transfer function under these parameter values of everything equaling 1. If that's our transfer function, what's h of j omega? Well, that's simply evaluating s on the imaginary axis, or replacing s everywhere, and in this case there's just one s with j omega, and we now have 1 over j omega plus 1. And what we want to do now is examine that as a function of frequency, both the magnitude and the phase, and you should already sort of be seeing that mental image as to what's happening. But what's the cutoff frequency? In this case, it's just the value of omega associated with the pole. The pole was at -1 in this case, and so our cutoff frequency is 1 radian per second. Our DC gain, when omega is equal to 0, is actually equal to 1. Now, we have a bandwidth of 1 radian per second, so that's our break frequency, and we have a DC gain of 1. So you can see what the Bode plot looks like. It's 0 dB, since log of 1 is 0. It's 0 dB until we reach omega c, the break frequency of 1, and then it falls off or rolls off into the stop band at -20 dB per decade. Well, that's not going to satisfy our design specs. We wanted a bandwidth of 100 hertz. Now, here, keep in mind that this is hertz and not radian per second. So now let's see what we have if we start with an initial transfer function with a bandwidth of 1 radian per second. We want to convert that into a transfer function that has a bandwidth of 100 hertz. So we're going to need to do some frequency scaling. And we need to be consistent. We need to work with omegas or f's, omega new, omega old, or f new and f old, but we just need to be consistent between new and old in terms of units. In our case, let's go ahead and just work in radians per second, since omega sub 1 is nice at that with those units. It's just 1. So now omega new over omega old is k sub f. That's our frequency scaling parameter. That's omega sub 2 over omega 1. I'm just trying to make sure that I use the right notation. But omega sub 2, that's our new bandwidth that we want, and we want that to be 100 hertz. Well, if omega 1 is in radians per second, then omega sub 2 needs to have those same units, and we can convert hertz or cycles per second to radians per second by remembering that 2 pi f now puts us into radians per second. So omega sub 2 is now 2 pi f. Omega 1 is 1. The units, radians per second, are consistent, so that now we have a unitless or a dimensionless scaling factor k sub f. It's now just some physical number, and that number is 200 pi, which is, remembering what pi is, 3.14, that's roughly now 628 as a scaling factor. So now we know k sub f, and we also know that we want a capacitor of 1 microfarad, and we now, in this particular circuit, have a capacitor of 1. So we know C sub 1, that's 1. We know C sub 2 is 1 microfarad. We know K sub F. Well, if we use magnitude scaling, now we have one adjustable parameter, K sub M, in this relationship between old and new capacitor values. And we can then use this expression to solve for K sub M given the information that we have. So K sub M, solving that equation for K sub M, is the initial capacitor, or the old capacitor, divided by the frequency scaling, which we just determined to be roughly 628, divided by, or C1 still divided by C sub 2, and C sub 2 is this 1 microfarad. Or we can now say that this is 1 over, carrying through a few more decimal places, 628.3, and C sub 2 is 1 microfarad, which is 1 times 10 to the minus 6. This now allows us to compute that numerical value, which in this case is 1,591.6. That's now our magnitude scaling constant, and resistors do have to be magnitude scaled. They don't have to be frequency scaled. So the new R1, that's the input resistor in this circuit, R1, and so that's why we might get confused with R1, R2 being new and old. So let's just say R1 new and R1 old, R2 new and R2 old. What's the new R1? Well, that's just a magnitude scaled old R1, or the scaling is 1591.6 times the old value, which is 1. So our new value for the input resistor is going to be 1,500, and let me get the ordering correct, 91.6 ohms. And the new resistor value, R sub 2 old, was 1. So 1 times 1591.6 is also 1,591.6 for the R sub 2, the feedback resistor. But if we go back to our design specifications, we wanted a gain of 2. And what is our gain, or what is our DC gain for these R's and C's that we presently have? Well, our DC gain in terms of R2 and R1 is just their ratio, and in this case, R1 new and R2 new are the same numerically, so their ratio is 1. Our DC gain is 1, or the gain in our circuit in the passband is 1, 0 dB. It's not 2. So here I've just answered this particular statement. Presently, the DC gain of the low-pass filter is 1, or 0 dB. We need a gain of 2. And we can adjust that gain by either adjusting R2 or R1 or both, because we know the gain is just their ratio. So let's look at this a little bit more closely. We can manipulate R1 or R2 or both to change the DC gain. However, remember what the pole was in terms of R1 and R2? Our pole location in terms of R1 and R2 is now this minus 1 over R2C. So if we change R2, C is 1 microfarad, we've now changed the bandwidth of our low-pass filter. So we can't really change R sub 2. It needs to stay the same. After being magnitude scaled, we don't need to frequency scale resistors. And we've already magnitude scaled to make sure that the bandwidth was consistent based on this capacitor expression. Which means then that we really shouldn't be changing R sub 2 to satisfy our gain condition. Let's now use R sub 1 to adjust the gain. The gain is R2 over R1, and we need that to be equal to 2. So we can solve that for R sub 1. R sub 1 is now half of R sub 2. And if R sub 2 was this 1,591.6, we take half of that, and we end up then with R1 being 795.8 ohms, and now we know what our parameters are. We have a R1, an input resistor of 795.8. We have an R2 that's 1591.6. And what's our C? Well, our C is what we wanted. C sub 2 was this 1 times 10 to the minus 6. And that is what we needed in our circuit because that's what we had coming off the shelf. And that now completes our design of selecting R1, R2, and C to have a first order low pass filter with a DC gain or a low frequency gain of 2 and a bandwidth of 100 Hertz.